All right. Welcome, everyone, to today's webinar on assessment and control of exposures to isocyanates in industrial coating applications. My name is Jessica Bunting. I'm the CPWR host and tech support for these events. Before we get started, I'm just going to go over a few quick things. If you're having any technical difficulties during the webinar, you can email me by responding to the WebEx reminder email that went out about 30 minutes ago. Or if you're logged in, you can send me a message in the chat box. If they're not already displayed on the right-hand side of your screen, you can add the chat and Q&A boxes by clicking on the buttons that appear toward the bottom of your screen when you move your mouse. If you have any trouble hearing through your computer speakers at any point, I recommend using your phone to call in instead for a clearer connection. We'll take some time at the end of today's presentation to answer questions. You can enter your questions in the Q&A or chat box at any time during the presentation, and we'll do our best to answer all of them at the end. Today's webinar will be recorded in full. I will automatically email that link to everyone after the event. You don't have to follow up with me separately. The PI of this project and our presenter today is Dhimiter Bello, Professor and Associate Dean for Research and Graduate Studies in the Zuckerberg College of Health Sciences at the University of Massachusetts Lowell. Thank you for joining me today, Dhimiter, and I will hand it over to you to get us started.
Thank you, Jessica. I would like to thank the participants who have taken time out of their busy schedules to attend the webinar, and I'm grateful to have this opportunity. And before I start, I would like to acknowledge my collaborators in this project, Professor Woski, Dr. Bello, Dr. Millet, Dr. Gore, and Yalong, doctoral candidates who have done a lot of this work, and numerous others who have contributed along the way. If there are questions related to clarity or methods, please drop a comment, and I will try to address them as I go along. I would like to read a disclaimer. Although we are willing to share the data with you, data that are presented here haven't been published yet. We are still cleaning up, refining the data set as well as the outcome of the statistical analysis, and therefore I would ask kindly that you do not share or distribute them widely, although you are free to use them as you see it fit in your daily activities. This project looks at isocyanates and epoxy-based systems in a variety of construction trades, spray polyurethane foam insulation, and we presented a webinar almost 2 years ago, now a year and a half. Then it's industrial coatings for exterior steel structure and bridges, interior floors and commercial buildings, caulks, glues, mortars, and other new technologies in the process. And today we'll focus mostly on industrial steel structure coating. The overall goal of the project is to utilize a data-driven approach and data to identify high exposures and to develop intervention strategies that will improve eventually work practices and reduce workers' exposures. So it is in overall sort of a holistic approach in what we are doing with these different construction activities. The primary have concerns of isocyanates largely related to their potent sensitizing potential. They are sensitizers and asthmagens. They are well known to cause upper airway and airway irritation, exacerbation of pre-existing conditions. In some rare cases, hypersensitivity pneumonitis can trigger severe asthma attack in sensitized people, even at low ppb levels. Isocyanates are also known skin sensitizers, and in a number of, they cause allergic contact dermatitis in about 25% or so of the cases, with the vast majority of cases being irritant contact dermatitis. They are irritants, and under certain conditions of high skin exposures, they could cause skin burns as well as burns in the eyes and respiratory tract if there are high levels of exposure. One interesting sort of link is between the respiratory and dermal exposure with sensitization, both with substantial animal evidence and empirical human evidence that dermal exposure may contribute to the sensitization of workers. I would like to take this opportunity to share with you a few papers that we published the past year that focused on exposures to flame retardants in SPF applications, as well as a testing outcome for protective garments from gloves to coveralls during spray polyurethane foam applications, and two publications that one summarizes exposures to and effectiveness of controls in SPF applications, which is under review, and another paper that's nearing the publication that reports on the evaluation of disposable protective garments in industrial coatings, which relates to a large extent to the data that I will be presenting today. That second paper, I'm presenting briefly a few results at the very end because they are relevant to the exposure assessment piece, but the details of it, I think, are best described in that paper. So the rest of this webinar is based on sort of presenting our findings and then discussing the implications with regards to isocyanate exposures in construction trades related to external metal structure coatings. Typical construction activities that fit in this category are tanks, storage tanks, such as the one on the left. It's a water tank. Wind turbines, parts for bridges and other sort of metal structures that are done indoors in spray booths. Reactor domes, as is shown in this picture here, and I would like to draw your attention to the fact that there are multiple colors, like a camouflage. Each of those colors represents a different layer and a different chemistry that goes into this multi-layer coatings. Bridge coating is perhaps one of the greatest sort of applications of these industrial coatings. They are done sometimes during the day, as in this picture to the left, and you could see this finished product here in gray, sort of greenish gray. Quite often they are done during the night, third shift, with active live traffic, and you could see here the containment around the bridge on one side of the road, and oftentimes in these applications, a containment is placed around the structure, not only during the first phase, which is steel structure ablation and cleanup, but for the rest of the process, because largely to protect steel structures and fresh paints from debris that would end up in the structures as a result of traffic and wind and stuff. Also, because of the requirements for technical specifications, most of these paintings require a minimum temperature and a certain relative humidity, which shouldn't be very high because then it would compete with the polymerization chemistry and the quality of the paint. So oftentimes in these containments, one would end up with environments that are both hot and humid, but not condensation. So the approach is similar to what we applied to the study of spray polyurethane foams, extensive workplace observations by trained both industrial hygienists and exposure scientists that capture relevant contextual information related to task duration, activities, layout, environmental conditions, products, collecting actual products, and when the opportunities arise, collecting information from the workers about how representative or typical the observation day is to their daily activities. We collect personal inhalation exposures. In this case, we have adopted SIP10 MI sampler, which is an inhalable sampler that uses a rotating cup, takes 1.5 to 2 ml of solution that uses, in this case, butyl benzoate, which is a non-volatile solvent, and 1,9-anthracenyl-methylpiperazine, or the MAP reagent that Dr. Bob Stryker at NIOSH developed and we have used for a long time. Dermal exposure, personal dermal exposures to hands by collecting gloves. As you could see here, we have used, to the extent that the workers have supported us, a glove dosimeter consisting of a thin medical grade cotton glove treated with the derivatizing reagent with thin nitrile glove underneath. So we typically ask workers to wear them at the beginning of the task and then ask them to hand them back to us or allow us to remove them to avoid the cross-contamination at the end of the task, which typically is in the order of half an hour to 2 hours. And then these dosimeters are transferred to a jar with an extraction solvent and derivatizing reagent, which is sealed and placed in a container. At times, the workers did not want to wear these dosimeters. They were too comfortable wearing their own gloves. And so in those cases, with these chemistries that are relatively slower compared to polymerization compared to aromatics, we have collected their actual glove, but that's a limited number of samples. We also collect urine, spot urine before the beginning of the shift, which in day shift would be around 7 a.m. or 8 a.m. And at the end of the shift, or when the workers would be willing to give urine, which may be before the end of the shift or slightly after the end of the task, several hours difference. And in the evening shifts, the pre-shift would be at 5 or 7 p.m., and then the post-shift would be typically between 5 and 6 or 7 a.m. And the night shifts, as one can imagine, are very challenging in terms of conducting the simultaneous inhalation, dermal, observational, and biomonitoring assessment. And access is challenging as well. For our spot urine pre and post, we measure urinary biomarkers for isocyanates, which in this case are diamines. We are working on other new generation of biomarkers, but I will not present data on that today, as well as monitoring of measuring of creatinine and specific gravity. All of these samplers at the end of the shift are put in cold coolers, kept away from light. We take good care of them until they reach the lab and are processed. So in this slide, metal structure coating, which is the focus of today's presentation, we have 10 site visits. About half of them or so are on bridges, 25 personnel samples, and several area samples, 31 glove pairs, and 53 urine pre and post, but total 53. I would like to mention briefly that so in these industrial coatings applications, the product is selected, at least for the Northeast, from a list of approved products that comes from the NEPCOAT list, Northeast Protective Coating Committee. And so there are 3 lists, A, B, and C, as well as there's a 4th one on inorganic primer, and they have specific recommendations about the type and composition of these coatings and the layers, as well as other specifications. There is some variety in the products that are selected. List A has 6 recommended products. List B has 22 products. There is more variety in the compositions or the chemistry of those products. Typical in these coding applications that is relevant to both the monitoring and interpretation of the data is that they are a 3 or 4 step process. Step 1 is surface preparation, typically ablation of the surface. Step 2 is application of a primer. Step 3 is a mid coat, which is almost exclusively epoxy. And step 4 is an isocyanate top coat applications. Sometimes we have seen in step 2 isocyanate-based mid coats, which are sometimes based on polymeric methylene diphenyl diisocyanate or polymeric MDI. And other additives, we have also seen polymeric TDI in a few cases, and paratoluene sulfonyl isocyanate, which is used as a sort of scavenger of moisture in these containers and to improve their sort of shelf life. Top coats are aliphatic isocyanates that are similar, quite similar in chemistry and performance to the motor vehicle repair industry. I also want to mention that in addition to the isocyanates that are used in these multiple coatings and the epoxy in between, Part B chemistry is rather complex and comes as a cocktail of sort of solvents, other solid additives, high concentrations of crystalline silica, titanium dioxide, zinc oxide, and the like. So although our focus is largely on isocyanates today, I do not want to lose sight of the fact that exposures could be far more complex. Briefly, for the non-chemist, typical of aliphatic isocyanates, we have hexamethylene diisocyanate, or HDI here, the dione, which is 2 molecules of HDI together, the HDI biuret, which is 3 condensed together and is a major component of these mixtures, and as well as HDI isocyanate. And these 4 molecules vary in their relative concentration by product type. There's a second category of aliphatics based on isophorone diisocyanate, of which there are 2 isomers of IPDI monomer, similar to HDI, and then there are several oligomeric species, 2 of which are presented here. So most of the paints that we've seen in bridges and structural coatings are based exclusively on HDI or polymeric HDI, and only in the case of floor coating we have come across polymeric IPDI. So I will simplify the talk by focusing largely on polymeric HDI, since no polymeric IPDI was found in most of these coatings. The analytical chemistry behind all the measurements is based on liquid chromatography with electrospray ionization and tandem mass spectrometry, oftentimes referred to as LC electrospray ionization, MSMS. We rely on mapped derivatives of all of these analytes. At the top, it's a typical totonyl ion chromatogram that you get out of a mass spec analysis of an isocyanate product, which is based on, this is a product rich in biuret. You could see the relative scale in this chromatogram does not translate to relative abundance of this species. For that, one has to look at the UV spectrum, but it has at the HDI, the dione, the HDI biuret, which is roughly 60+% of the total isocyanate, and small amounts of the HDI isocyanate. And further back here, there's another compound that's a diisocyanate. The detection, so at the bottom, there's another product which we have seen in floor coatings. This is distinct from the first one in that this one is largely based on an HDI isocyanate component, and it has polymeric IPDI. The detection limit for all of this is in the low nanogram to 5 picogram or 50 picogram per ml. So 50 to 150, 800 picograms, 900 picograms. And so then these are big molecules, so 900 sort of picograms is not a large number. So the point is we have plenty of sensitivity in these analyses. Now I'm moving slowly to the results. So in this slide, we summarize sort of the types of personal protective equipment used across these different sites. With regards to airborne exposures, about 30+% of people who we observed and sampled did not wear any respirator. That could be during rolling applications or if they were bystanders. And the majority of them would wear full half-phase organic vapor cartridge, sometimes with but often without a particulate air filter. In terms of gloves, about 80% or so, close to 20% would not wear any gloves, and that would include rolling and brushing applications, painting with the roller or brush, mixing, and as well as inspecting and doing cleanup work. And the most common glove type was either a nitrile glove, about a quarter of the cases, or polymeric coated on the palmar side and thick cotton or some other polymer sort of fiber on the top, which are the typical gloves you see at sort of these Home Depot or Ames stores. And so they it appears that workers like those types of gloves because of dexterity that they provide. In terms of coveralls, standard clothing was quite common in half of the people. So because of high heat, high humidity, and high physical demand of such activities, workers would just opt not to wear a Tyvek or some other coverall. In some cases, we saw workers wear thick cotton fabric coveralls, and in about 20% of the cases, a polymeric coverall such as Tyvek or polypropylene. In terms of personal breathing zone exposures, for simplicity, I'm presenting the two analytes here, the HDA monomer panel to the left and the HDA bioret panel to the right. The monomer is relevant in that biomonitoring for this species relies on HDI, at least what we have so far, whereas the HDI bioret is one of the major sort of components of these paints, and stratified by helper or the actual painter. And you could see that concentrations here in the case of painters could get quite high, from anywhere between close to 60, 70, 100 microgram per cubic meter, all the way up to close to 0.91 milligram per cubic meter of air. That's very high for a monomer like HDI. In terms of the bioret, we are routinely in the range of 1 to 8 milligrams per cubic meter. Now, just as a reference to concentrations we get in spray polyurethane foam applications, there we are in the order of 1 to 100 microgram per cubic meter. Here we are in the milligram range. These are very high, and isocyanate similar, and the dione in between the monomer and these higher oligomers. So these actual concentrations, not adjusted for time without exposure or not taking into account PPEs and so on, just straight interpretation of these numbers, about 20% of these measurements exceed the NIOSH relative exposure limit for a time-weighted average, the whole day, of 35 microgram per cubic meter of air, 17% higher than the ceiling limit. And what is interesting here, that all samples that were that exceeded these levels belonged to two sites, and they both were enclosed sites, like the one I presented, and one that was one of the actual sites, and both happened during the summertime and daytime, where temperatures were quite high. Again, looking at distribution of personal exposures as a function of site, whether it's on bridges or reactor domes or wind turbines. So from enclosures to wide open 300 feet above the floor, we see panel on the left, again HDI, panel on the right, the bioret. The highest concentrations reaching as high as 250 roughly microgram per cubic meter of air in bridges, with a value close to 1 milligram per cubic meter at the very top, the outlier. And then on the right, similar picture with higher concentrations of the bioret in indoor sort of spray booths. If we look at concentration of this isocyanate as a function of actual task, whether it's spraying with a spray gun, rolling or brushing of these structures, and there's a lot of sort of painting with a roller or a brush in bridges so that the workers can reach out to these delicate spaces that otherwise spray painting would not cover. So again, perhaps no surprise here, the highest concentrations relate to spraying, but we have seen some, substantial concentrations of, you look at the HDI as well as some of these higher oligomers for rolling application. And we suspect this has to do with the generation of aerosol droplets that are thrown out into the air. Whereas for HDI, we also think that may have to do with high temperatures and low vapor pressure of HDI, so evaporation. In terms of personal dermal exposures, this table sums up the exposure distributions for the different species, the monomer, the bioret, isocyanate, the dione at the very last row. We start with sampling duration. Typically for gloves has a median of close to 2 hours, 118 minutes, with a range of up to 4 or 5 hours. The concentrations, so we have anywhere between 0% to 60% of these species non-detectable, and part of that is because HDI, they may be non-detectable because the product did not contain that species because of the variability. Some have no dione, some have small amounts of dione, some have no isocyanate, and some have high levels of isocyanate. So the 60% implies that these particular species was not found in the samples. It does not mean that it was below the detection limit because we cannot measure it. It's because in many cases it wasn't there to start with, and we know that from analysis of the bulks from the site. And there may be other reasons for that as well. But looking at the actual numbers, we are looking at geometric means of about 200 micrograms per pair over, and if we sum it across all species, we are in the order of a milligram or so. You look at the ranges here, the maximum in a number of cases is in the order of several milligrams, and in one case, close to 61 milligrams of isocyanate of actually HDI bioret, only this one. This is massive dermal exposure in terms of the amount that you have on these gloves, and so it's considerable, and especially if you think that that glove was there in use for only an hour or no more than 2 hours. Urinary biomonitoring for aliphatic isocyanates continues to be a challenging task, in part because, well, right now we have, for 2 decades, been using the hexamethylene diamine, HDA, which is the hydrolysis byproduct of HDI, to measure. I am aware that more recently there have been some developments to finding and quantifying other equivalent hydrolysis byproducts, such as the corresponding triamine of biuret or isocyanate. I won't get into discussion on that right now. We'll talk at the very end. But HDA has been, or IPDA for the IPDI, have been sort of the only thing we could work with in urine. And so we start with HDA, which is an established marker. In terms of the results, the first two columns to the left are pre-shift concentrations and post-shift normalized to specific gravity, and the other two are normalized to creatinine. Normalization to creatinine is a common approach, and debate continues in the literature as to whether it is the right way or not. In some cases, it is fine. In other cases, such as here, it may not be okay, and I'll talk a little bit more about that. But we have done normalization according to both methods, and so what we have here is mid, median, max, geometric mean, geometric standard deviation. We look at them, but so normalized to specific gravity, we see almost tripling of the geometric mean value of HDA post-shift relative to pre-shift, and a more modest increase when we normalize to creatinine. We have a good idea as to why that's the case, but we see a clear increase cross-shift, and normalization to specific gravity makes that contrast bigger. And also, we are mindful that this is only for HDA. If you look at the distribution of specific gravity in urine for the population of workers pre-shift and post-shift, about 77% of all the urine measurements are above what is considered a normal specific gravity for well-hydrated individuals of 1.02, and at the end of the shift, that number goes to 80%. So dehydration appears to be, continues to be a major thing with these construction workers on construction sites, especially on bridges. Several of the sites that we measured, temperature outside was 90 to 110 Fahrenheit. In one of the cases, they stopped working because of imminent heat stress concerns. If you look at creatinine distribution pre and post shift, there is an upper normal value that WHO recommends of about 300 milligrams creatinine per deciliter for 100 milliliters. And about half of those workers would exceed that upper normal level at the beginning of the shift. Again, that goes along with a dehydration concept. But then at the end of the shift, that number will be over 80%. And so this huge change in the amount of creatinine produced post-shift reflects both increases in the level of dehydration or concentration in urine, but also reflects physical activity. However, the challenge is that we see this huge change cross-shift, and then when you normalize to creatinine, you suppress that cross-shift difference in the urinary biomarkers. So here, we are looking at the difference in HDA cross-shift, normalized to specific gravity to the left or creatinine to the right, and one would expect, based on the previous set of slides, that this difference will be statistically significant in the case of specific gravity and borderline in the case of creatinine adjustments. So for HDA, there is a biological monitoring guidance value established by the Health and Safety Executive, equivalent to 1 micromole HDA per mole creatinine, which is the same for MDA, the biomarker for the polymeric MDI. Now, if we compare the cumulative distribution of urinary HDA measurements to this BMGV value, about 60%, 58% of all urine samples would exceed that 1 micromole per mole creatinine value. About 28% would exceed the 2 micromoles, double, and about 10% would increase the 4 micromole. So we have two sort of notable observations here. The first one is that the number of workers with a high sort of urinary HDA value is quite high, and there's a subgroup of them that it's considerably higher and reflects substantial uptake of isocyanates. And looking at pre and post shift, there's a considerable number of workers who have elevated levels of these urinary biomarkers at the beginning of the shift, the interpretation of which is that this is a carryover from prior days. Now, if we look quickly at how urinary biomarker values differ as a function of PPEs and tasks and sites, we see here, perhaps not surprisingly, that people who wear respirators have a considerably lower urinary HDA value. Although not statistically significant, we can attribute that to huge variability in processes that we've studied here, as well as other exposures, including dermal. But people who didn't wear respirators have a much higher value. And if we look at the clothing, cotton coverall is sort of a coverall made of a regular cotton sort of fabric, or standard clothing, which is that varied quite a bit, actually, hard to summarize, but thin or thick sort of fabrics, t-shirts, sweatshirts, and oftentimes the forearms didn't have anything. They're completely exposed skin, exposed neck, exposed faces. But people who wore a Tyvek type of coverall had notably lower biomarker levels, which in the context of permeability of isocyanates through these fabrics, this seems to make sense to us. When you look at whether there's any trend on these urinary biomarkers as a function of the types of gloves, here things are all over the place. It's difficult to make sort of a generalized observation, and part of that has to do with, I think, the fact that it's not just hands that contribute to uptake. We also have respiratory exposures and also whole body exposures and uncovered body parts like forearms and neck and face. So one of the sort of findings related to dermal exposure, which also is supported by our own observations in the field, has to do with the fact that there's massive both potential for dermal exposure, but also significant dermal exposure. And we failed to bring some pictures which showed sort of exposed hands covered with these isocyanate paints. But we have seen that frequently. And so we were compelled to prepare us to sort of work, develop a method, and look more formally at the permeation and penetration of these types of paints through different types of fabrics. Dr. Mellet spent several years developing these techniques and also painting. And at the end of those 3 years, we gave him a certificate as an excellent painter. And so I'm presenting here a couple of slides from one of his papers, which is currently under review. To the left, we have a positional spray gun that has a fixed sort of stroke distance and ensures good reproducibility of this painting sort of style on different fabrics which go onto these permeation cells. The method is the modification of what Professor Yost at University of Washington in Seattle used with Diana Sebajos a few years back. We had to modify it so that we could make it work with the types of fabrics and highly viscous paints that we were dealing with here. We worked with 5 different garments, 2 types of gloves, latex and nitrile, the thin nitrile gloves, the ones that you grab in these regular stores, and 3 types of clothing, including 2 types of coveralls, Tyvek or polyethylene, polypropylene, as well as a cotton shirt, which was commonly used in, we saw it in this in the field. And we tried 2 products. One is a zinc-rich primer, comes from the NEPCO list. It's based on polymeric MDI, highly viscous product with high content of solids, and the other product with an aliphatic finish, which is the top coat. This is a busy slide, but I will try to walk us through it. So what we have here is 4 panels. The left panels, top and bottom, relate to the primer, zinc primer of polymeric MDI. The right panels, top and bottom, relate to the top coat, which is a polymeric HDI product. The top panels, left and right, relate to gloves. L stands for latex and N stands for nitrile. The bottom one for the coveralls. C is the cotton fabric coverall or shirt. And T is Tyvek and P is the polypropylene or polyethylene. And so we have, so the experiment was spray with a fixed amount, relatively reproducible, and then collect on a filter on the back of the fabric at different time points, and then calculate a permeation rate. Penetration, which is the free movement of paint across holes, would be assessed based on some dyes that we use for that purpose, and that is immediate. So in both cases, and consistent with Mike's earlier work, nitrile gloves, these are the thin ones, do a fairly good job of sort of protecting from penetration of isocyanates through. In the case of polymeric MDI, nitriles are better than in the case of the aliphatics. Part of that may be the presence of solvents, but these are the data. And latex have been used in some sites, actually, to our surprise. In the case of coveralls, again, the Tyvek appears to be much better than polypropylene P or PP in the case of polymeric MDI, zinc primers, less so in the case of this other sort of aliphatic finishing. The cotton T-shirts, they do provide, if you look at the actual numbers compared to breakthrough and loading, quite a bit of protection. So they provide some protection, but they have big holes, and so relying exclusively on them, as it is sometimes done in the field, it's not a good practice. But adding them as a secondary layer adds some additional protection. If you look at the bottom left panel, in the case of cotton T-shirts, we have immediate rapid penetration in the first 5 minutes, as seen by these very high concentrations of isocyanates measured immediately, almost within a minute or so of this testing. So the message from this testing is that nitrile gloves are superior, and this is a consistent finding across this study, our prior study, and the findings of Dr. Yost's group a few years back. 5 mil nitrile gloves would be desirable, so that the thicker ones, because they don't tear as easily. Whereas in terms of coveralls, the answer is it depends, but generally Tyvek type of coveralls or polypropylene, polyethylene are the better ones. So what is the sort of the main take-home message from these findings? Well, we believe, based on quantitative measurements, field observations, that there is a significant potential for dermal exposure as well as considerable actual dermal exposure. We have observed quite frequent contamination of surfaces and tools with isocyanates, contamination of skin and surfaces from overspray aerosols. And these are paints that do cure a lot slower. They are sort of still not solidified hours later. They have half-lives of like 8 hours or so, several hours during the day. And also, the common sort of pathway of dripping of paints during roller brushing, etc., that we know very well from doing such things at work, so at home. High airborne concentrations based on the findings, so average concentrations anywhere from a few hundred micrograms per cubic meter to milligrams per cubic meter. These are the highest concentrations our group has measured in many years, especially in enclosures, in bridges. Because of the high temperatures, this work is done during the heat summer days. Hot metal, that the richest temperatures that are burning to the skin on contact. The respirators, given high concentrations of these isocyanates, given these other conditions, relying on an OVC type respirator seems to be a little bit of a problem, although we understand the challenges of other selections. Urinary HDI biomarker levels overall quite elevated and elevated pre-shift as well as cross-shift. Quite a high number of samples, urine samples, exceeding the biological monitoring guideline value, which is considered a threshold for good hygiene practices. So above 1 implies that, and the further away you are from 1 implies that hygiene practices in the workplace can be improved significantly. These numbers are much higher than what has been reported in the literature in the motor vehicle repair sector, which is from 2 to 25% of urine samples in prior studies exceeding this biological monitoring guidance value. So construction appears to have much higher exposures. I am quite mindful of the challenges of relying on urinary biomonitoring for HDI to draw conclusions across more complex exposures. And so based on some preliminary work as well as new sort of research that's coming into the public domain, I do believe that we have reached a point where within the next few years we will see a new quite novel biomarkers of isocyanates that are a lot more specific to this species, a lot more sensitive, and require much less sample processing time. And I've mentioned 2 here, the work by Dr. Nylander-French, as well as the work by my collaborator, Dr. Wisniewski, with glutathione adducts and dilazine adducts that have just become apparent. So I do believe that we need to go back to the samples and work with this new set of biomarkers, because that will provide a more robust sort of assessment of relationship with different exposure pathways, as well as the PPEs. Although our overall interpretation of such data is that, well, there's plenty of room here to improve work practices and reduce exposures. And so I would also like to mention, based on our observation, that in addition to sort of isocyanates, we need to look at part B, as well as this nexus of physical stressors such as dehydration, based on the data we have, heat stress, based on observations we have, mixed chemical exposures coming from part B on top of the isocyanates, and this very high, very concentrated urine samples and extreme dehydration, it makes me personally worry about the impact it has on the kidneys. And so I personally think we got to look at that more, a little bit more closely. And the most important thing is that there are opportunities for interventions, which is the primary goal of this work. So with this, I would like to express my sincere thanks to our contractors and workers and various colleagues and our graduate students, and special thanks to Dr. Stryker at NIOSH, Dr. Kate Jones at HSC, Dr. Wisniewski and Redlick at Yale, who have been supportive of us for many, many years, and who we consult with at times for both interpretation of the data and as well as for improving the science that we do. And with that, I would like to thank you all for your patience and for taking, again, time out of your busy days to listen to this webinar. And I look forward to some Q&A. And again, feel free to reach out to Jessica, reach out to us, and we'd be happy to share the data or the information we have. And most importantly, to some of you who are dealing on a day-to-day basis with the health and safety aspects of these applications, or who make decisions about what types of PPE to use and what types of practices to adopt, or whether you worry about or wonder about what concentrations or exposures these workers may be getting, we ask, we beg that you get in touch with us and help us get access to this site so we can improve the data set on which we base the decisions and the recommendations. And with that, thank you to all again. And Jessica, this is back to you.
All right. Thank you, Dr. Bello. And we have been getting a few questions in, and if you have others, please submit them now. Our first question is, will a copy of the presentation be available? And I did mention that I will send out a recording of the webinar, but since the data has not been published yet, we are not sharing the slides directly, but you can feel free to reach out to Dhimiter or myself at the contact information on the screen, or just by responding to one of the WebEx emails, and we'll work with you to get the data you're interested in. All right. Did you look at how each type of respirator impacted urinary markers, or did you just look at yes, any respirator versus no respirator?
I think because the number of samples is not that large, the level of analysis, at least that one we presented, was yes or no. But I'm trying to get the slide that would answer here. So if you look at we're on slide 16, we had the majority of respirators, 60% was half-phase or VC. And so we had only like 2 or 3 respirators that would fit in the other category. And so the numbers are really small for a robust statistical analysis.
Okay. Our next question is, maybe I missed this, but is the CIP-10M sampler readily available now for field industrial hygienists, or is it essentially still a research tool? Are there commercial labs that can analyze the sample or sampler?
So the sampler is commercially available. At least in the Northeast, we have a distribution point here in Chelmsford, Massachusetts. Ani can get you the contact information. It's an expensive sampler. It's like over $4,000, $5,000 a piece, so that's a challenge. The workers love to wear it, and we have been fortunate with using it because no other sampler would would resist those harsh environments and the knocking around and tumbling of the workers as they do these jobs. With regards to analysis by another lab, well, the chemistry we use is restricted by the reagent, the MAP reagent. And so there aren't many labs that are doing that. It's us and Dr. Stryker's lab at NIOSH, they're contractors. But I do think that in terms of the aliphatic isocyanate monitoring results, equivalent data could be sort of generated using samplers such as the ASET sampler for aliphatics, and based on prior work we've done in the past and comparison with the reference samplers such as impingers, one could also use a treated filter and with field extraction, although I think the ASET sampler or a SIP10 would be, in terms of the design, the more sort of superior samplers for this particular application.
Okay.
This answers the question.
Sorry? Oh.
I hope this answers the question.
Yes. Did any workers, do you know, wear airline respirators?
I think that I have seen only one case, or I was told of only one case where you supplied air respirators on wind turbine application, but I was not allowed to go up there at 300 feet, and the person did not wear the respirator, so that's why he doesn't show up on the statistics. But we have not, we did not wear the sampler. We have not seen supplied air respirators anywhere on all other sort of sites. It has been exclusively overseas. And this is in contrast to spray polyurethane foam, where almost half or more of sites would rely on supplied air respirator.
Okay, thank you. Great. I think that's all the questions we had. If anyone has a question that we didn't answer, or you think of a question after the event, again, feel free to email Dr. Bello directly or reach out to me through any of your WebEx emails or through the follow-up email that I will send with the recording of the event. And thank you again, Dhimiter, for a wonderful presentation today.
Thank you to you, CBWR, and all the participants for giving us this opportunity. Thank you all.
Take care.
Bye-bye.